antimatter. That word probably conjures up images of Star Trek or Doctor Who, but perhaps that's because antimatter is just rare, just elusive and so far removed from our everyday reality. But far from being science fiction, antimatter is science fact, and its nature is of huge importance to us, because the behavior of antimatter could let us understand how the universe evolved, if only we could understand it. And this discourse is all about antimatter from the deepest, most fundamental point of view, the point of view of particle physics. I'm going to tell you what the universe consists of, what matter consists of at the deepest level, and how antimatter fits into that picture. I'm going to tell you how little we actually understand about antimatter and how we're trying to redress the balance through experiment. I'm going to tell you about 3 very, very different ways of looking at antimatter and examining it that are our current experimental thrusts today. And I'm going to give you our latest results so you can see for yourselves how close we're coming to understanding the whole thing. Okay. Before I launch into antimatter, though, I had better set the scene by starting off with the universe and what we understand about matter. And everything that we understand about the universe from a physics point of view is summarized on this time history that you can see behind me. So we think that the universe started in a Big Bang, a hugely energetic fireball that brought everything we see around us into existence. And the very early universe was a very, very different place to the universe that we know now. It wasn't full of galaxies or stars or even atoms. It was populated by the ingredients of atoms, fundamental particles. Now, as time marched on, the universe expanded and it cooled down, and after various points, it became energetically more viable for this matter to start to clump together into new forms. So after a few fractions of a second, we had the first protons and neutrons. After the first 300,000 years, we had the first atoms, and then larger and larger scale structures, stars, planets, galaxies, and then almost 14 billion years later, you get to us asking the question about what happened. Now, that's what we think happened, but how we know any of this is through experiment. And it's fairly straightforward to work out what the universe is doing now and what it's made of, because you can look at it through telescopes. You can send out probes to take measurements of anything that's close enough to you. And this is the realm of astrophysics. But if you really want to understand the universe, you also have to understand how it got here, how it evolved from the Big Bang onwards. And that presents a problem, because you can't look at the very early universe. It's opaque, before 300,000 years old, before atoms formed. So if you want to understand that, you have to recreate those very hot conditions in the laboratory to look at them. And that's what particle physics does. That's what particle physics does in particle accelerators, and that's how we fill in our knowledge of that part of the universe's history. And that also, coincidentally, is the part of history where antimatter makes the biggest impression. So we've understood quite a lot about the universe and what it's composed of through our experiments. We understand that matter is composed of no more than 12 types of fundamental particle, 6 quarks, 6 leptons. And these, by the way, when I talk about fundamental particles, these are tiny. They're at least as small compared to atoms as atoms are compared to you. And I say at least as small because they're so small that we haven't yet been able to measure their size. They're just smaller than we've been able to measure. It's a limit. Now, what holds these tiny, tiny objects together to make matter look the way it does to us are a small number of fundamental forces. There's the weak force. That's responsible for radioactivity, and it affects every single one of our matter particles. And it's conveyed by force-carrying particles, particles called W and Z bosons. And we even have a picture for how this works. We think this force, and others like it, are conveyed by these force-carrying particles being exchanged between matter particles. And this is what does the sticking together, so to speak. But it's not just the weak force that does this work. There's also the electromagnetic force. That's much more familiar to us in everyday life. It's driving the lights, it's driving my laptop and the projector and so forth. You all know about the electromagnetic force. You know it acts on anything with an electrical charge, and that means it also acts on any fundamental particle that's charged as well. And it's communicated by photons of light. And then quarks, and this is what makes them different to leptons, also feel something called the strong force. And it's the strong force that keeps atomic nuclei stable, because it's an attractive force, and it's strong enough to overcome the electrostatic repulsion that protons, positively charged protons in the nucleus, would otherwise find and feel. Now, that is about it, to be honest, for everything that we consider in particle physics, but it's not all there is to understanding the universe. There's one more force, gravity, which is extremely important for understanding the large-scale structure of the universe. Now, gravity acts on mass, and we know that our fundamental particles have mass because we've measured this experimentally. However, gravity is so weak compared to the other forces that it doesn't really enter into our picture of the universe at these very tiny scales and these very early times. That's also because, not just because we can discount its effects, but because we haven't yet found a way of describing gravity in the same way as the other forces, using the same branch of mathematics. That hasn't worked for us yet. Okay, so we have matter, and we have force that sticks matter together. And there's just one more ingredient in the universe, and it's one that was discovered very, very recently, just over a year ago. And it comes back to this question of mass that I've just mentioned in the context of gravity. And it's to do with the reason why fundamental particles have their mass in the first place. And we think that's due to the Higgs field. Now, the Higgs field, if you can imagine, is a kind of energy field present throughout the universe. And we think it gives fundamental particles their mass as they move through the field by interacting with them as they go. And the amount of mass a fundamental particle gets depends on how strong that interaction is. And this field, like the other forces, has a particle associated with it, the Higgs boson. And with that final piece in place, our whole jigsaw of the universe is completed. And we not only have identified all these different components of the universe in terms of matter and force and the Higgs that gives particles mass and have a picture for how it all works, but we can encapsulate these pictures mathematically in equations. And these equations form our theory of particle physics. And this theory is so elegant, so mathematically succinct, that you can write it on the front of a T-shirt. You can even buy the T-shirt if you go to CERN. It's a retail opportunity that awaits you. But more than looking good from the point of view of a mathematician, this theory is really special. It's so good that we haven't yet made an experimental prediction a theoretical prediction that disagrees with anything we've observed experimentally. It's so good that we call it the standard model of particle physics. So here we are. We have a very simple universe at its core and a very good theory that describes what happens. But that's only half the story. Unfortunately, I've only told you half the story, because for every single one of these particles that I've told you about that's described in the standard model, each one of these particles potentially has a twin, an antimatter version, a counterpart that behaves like a mirror image of its matter counterpart, but carries the opposite electric charge. So the antimatter equivalent of the negatively charged electron is the positively charged proton. The antimatter equivalent of the positively charged proton is the negatively charged antiproton. Now, the hallmark of antimatter, how you know you have it, is that when matter and antimatter meet their opposite counterparts, there's one diagnostic that lets you know that's happening. Because matter and antimatter otherwise are pretty identical. And that's because when they meet, they annihilate, and they release enormous amounts of energy. If I have a 1/4 gram of matter meeting a 1/4 gram of antimatter, the resulting annihilation has the explosive force of 5 kilotons of TNT. It's completely noticeable. It's a completely good diagnostic that you have antimatter in the vicinity. Well, luckily, that doesn't happen very often. And in fact, it happens not at all. And so you might be wondering what part antimatter plays in the universe, because there's not very much of it around. You might be wondering why we should even want to have antimatter in the first place. And that wouldn't be a stupid thing to say, because for the vast majority of mankind's history, antimatter wasn't even dreamt of. There was no reason to have it. And that's because if you go back to classical physics, and let's say you want to describe the motion of something simple, like an electron, there are very, very simple equations that do the job for you. They're equations like the ones on the screen behind me that define the energy, the kinetic energy of an electron, the energy it has by reason of its movement and its speed, its velocity, v, or its potential energy that you can relate to the height. Now, if you have an electron, if you have any electron, and you take its energy, for example, and its velocity, you'll always get the same answer out for its mass, because electrons have a characteristic invariant mass. There's only one solution, in other words. There's no need for any other solution or any other types of matter. Now, that whole situation changed in the early 20th century, when people started to realize that these classical equations of physics didn't apply in every single situation. And the first clue that they weren't complete came with Einstein. Einstein was studying the movement of things going very, very fast, close to the speed of light, and realized that motion diverged from classical equations. You had to treat things slightly differently. And so he derived equations of motion, the special theory of relativity, that still related energy to momentum and speed and mass, but did it in a slightly more complicated manner, but one which was more generally correct. And that wasn't the only thing going on at that time. Quantum theory was being developed. Quantum theory is the physics of the very, very small. And when I say very, very small, I mean atomic level and below. Because at these scales, classical equations and physics also don't work either. They start to break down and move away from the behavior that you observe. So quantum theory was being developed as a better way to describe atomic level and subatomic level objects. Now, one quantum theorist, Paul Dirac, worked on unifying quantum theory with Einstein's theory of special relativity to derive the equations of motion for an electron that were most correct and most general. And his work culminated in this equation. It's the Dirac equation, named after him. It unites the theories, so the psi, the sort of candlestick-looking thing you can see in the expression, that's what's called the electron wave function. That's the object in quantum mechanics that describes everything we know about the electron, every question we can ask about it, its position, its speed, and so forth. The information is contained in that function. Einstein's equations of motion of special relativity are contained in this gamma mu, d mu, couple of symbols. It's such an elegant equation. And to Dirac, this equation was absolutely beautiful. So beautiful, it had to be true. And it was true. It did describe the motion of an electron, and it did it exceptionally well. So well that you could also use this equation to describe the light that came out of atomic spectra of hydrogen when electrons changed their energy levels. There's just one catch with this equation, which was that it had twice the number of solutions that you would expect. One solution described the electron, and the other solution appeared to describe something identical to the electron, but which had the opposite electric charge. Now, other quantum theorists were working on the same problem and hit the same problem of two solutions. And the majority of them suspected that the second solution, because it didn't correspond to anything in reality, was just a sign that maybe quantum theory wasn't right, that quantum theory perhaps wasn't mature enough to really describe the universe, and the second solution had to be ignored. But to Dirac, this equation was so beautiful that it just had to be correct. And that meant that the second solution had to be physical too. It was too good not to be. And this debate raged for about 4 years until a man called Carl Anderson ran an experiment looking at cosmic rays from outer space. Now, cosmic rays are just high-energy particles that come in from the solar system or extragalactic sources, and they impinge on the Earth, and they go through the atmosphere and hit the Earth's surface. In Anderson's experiment, he had a cloud chamber, which is a box about so big, and it's filled with a supersaturated liquid. And when you have a charged particle going through this liquid, it ionizes it, which seeds a vapor trail. And you can photograph the vapor trail. And there's a photograph behind me. And cleverly, if you put this in a magnetic field, you can bend the path of the charged particle to the left or to the right. And this tells you whether you have a positive or a negatively charged particle. In this photograph, what Anderson realized he had from the track that you can see passing through like this. This track had the amount of energy deposited that was absolutely characteristic of an electron, but it curved the wrong way. It had a positive charge. So in fact, what Anderson had here was the first photographic evidence of antimatter, of the positron. And with this discovery, then antimatter was on the map. We knew it existed, and in fact, we knew at that point that it existed not just for the electron, but because Dirac's equation was equally applicable to all sorts of fundamental particles. All sorts of fundamental particles had their antimatter versions too. So it's only been since 1932 that we've really taken antimatter seriously. No one had dreamt it up before then. It's just something almost magical that fell out of an equation when you weren't even looking for it. A total surprise. So great, why is it so interesting? Well, it's so interesting because of its implications for the early universe. And this is something that Dirac's equation didn't tell us. According to Dirac's equation, matter and antimatter should behave exactly identically. But we've realized that's not the case. And we know that because if you go back to the beginning of the universe, the Big Bang, we think that half of the universe at that point was made of antimatter, half of normal matter. And if you can picture it in your mind, this very early universe was a seething mass of matter and antimatter, fundamental particles meeting, annihilating, releasing photons of light that then split into new pairs of matter and antimatter particles that met, annihilated, and so forth. And this whole process continued as the universe expanded and cooled until eventually, maybe a few seconds after the Big Bang, the universe had expanded and cooled so much that it was no longer possible for these photons from the annihilations to make new pairs of matter and antimatter particles. And that whole process of annihilation stopped at that point. And what remains in the universe now, anywhere we look, out in space, any direction, is a consequence of a very, very tiny difference that existed between the amount of matter and antimatter that we had at that time. I mean, very, very tiny, something like 1 part in a billion. But that tiny difference is the reason why we're here. We are the leftovers from those collisions. Because if there were equal amounts of matter and antimatter at that time, they would all have annihilated, and the universe now would just be full of light. So quite clearly, antimatter is something that we have to take seriously if we're going to understand the evolution of the universe. So how can we get from a universe that's half antimatter to a universe now that's matter-dominated, where we hardly see any antimatter at all? Well, to get from one to the other, you need to have more matter than antimatter. That goes without saying. But that can only happen if there's some difference between matter and antimatter, if there's some difference in the behavior of matter and antimatter that meant that after a few seconds you ended up with more of one than the other. Now, technically, that difference is something we refer to in particle physics as CP violation. All that means here is C and P are the two things you do to matter to turn it into antimatter. C stands for charge, you change the electrical charge. P stands for parity, that's the reflecting it in a mirror bit. Now, according to Dirac's equation, matter and antimatter behave the same way, so they had complete symmetry under CP. But that can't be the case if the universe changes from being half antimatter to now. There has to be a violation of that symmetry. There has to be a difference. Now, it's a very subtle difference, and I want to give you a type of visual analogy for the sort of subtlety that's involved. And it's only an analogy, so I don't want you to take it too seriously. I just want to give you an illustration of the very slight differences that we're looking for. So, in my analogy, my bit of matter that I'm considering is represented by this Escher picture. I want to turn this into its anti-picture, just to illustrate the idea that I have in mind. Now, I have to do two things to my picture to turn it into an anti-picture. The first thing is to reflect it in a mirror, because my anti-picture will behave like a mirror image. Well, that's easy. I can just reflect it. And I put a little P there to remind me. That stands for parity. The other thing I have to do to my picture to turn it into the anti-picture is to change its charge. And this is where my analogy breaks down, because the Escher picture is not electrically charged. But I can represent electric charge by changing black to white, white to black, and altering the direction of my grayscale, if you like. So let's do that and see what happens. Okay, so that's what happens when I represent changing charge. Now, to turn my picture into my anti-picture, I have to do both things together. It doesn't matter what order I do them in, one after the other. I'll end up with the same thing. And here it is in the bottom right-hand side. That's my anti-picture. Now, according to Dirac, that anti-picture should look identical to to the matter picture originally. And it does look pretty similar. But if you look closely, in detail, then you might see some subtle differences in shading. You might notice that the shading on the wings of the geese is slightly different between matter and antimatter. You might notice that the shading in the fields is slightly different between matter and antimatter. In other words, the nature of antimatter and matter isn't quite the same. And it's that very tiny difference, that's the visual analogy of the very, very tiny difference that we want to discover and understand in particle physics. Okay, so that's why we have antimatter, and that's told you why antimatter is so important. So now let's go on to the big question, which is, how much do we understand about antimatter? Well, I've summarized it here. Not a lot. Not a lot, if I am really honest. And that's because we have no underlying explanation for why antimatter should be different. We almost had no expectation that antimatter should exist, and that only that equation that predicted it, well, that's our only theoretical input, and that predicts matter and antimatter should be the same. So it's very hard to try and make progress. Now, we have observed experimentally that matter and antimatter are different. Observations were made in the 1960s that showed this to be the case. So although we don't have a deep underlying theoretical explanation for why antimatter is that little bit different, what we do have in the standard model is a parameterization of this difference that we had to add on to the theory in quite an ugly way to make it fit experimental data. That's the only theory guideline we have. But at least it's a prediction that we can test by making more and more and more and more measurements of matter and antimatter and how they're different, and then seeing if they match the theory. And if they do, we know that this parameterization works. Even if it doesn't explain, it works. In other words, then, our search for the nature of antimatter is going to be driven by experiment. And so our hope is that by making as many measurements as we can see the deep pattern under the measurements. We can see the big picture that they all add up to. And that will help us understand, finally, why antimatter behaves the way it does. And that might also help us understand the universe in a much deeper way. So now I'm going to switch tacks. I've told you why antimatter is important. I've told you why we have it. Now I want to tell you how we're trying to understand it. And that means I'm going to start telling you about the experiments that we run to try and understand it. And I'm going to give you 3 very different ways of looking at the whole subject. Okay, so the first way is to step back a little bit and think, well, we don't see much antimatter around us here on Earth, but maybe it's out there in the universe somewhere. maybe we just haven't seen it because antimatter annihilates on its way through the Earth's atmosphere, and that's why we never see any around us here on Earth. So the obvious solution here is to look in outer space. Maybe outer space holds the answer. And these cosmic rays I told you about, these high-energy particles from outer space, well, perhaps there's more antimatter there than we thought. So if we can only put an experiment up into orbit around the Earth, we can make measurements of it and perhaps see evidence for more antimatter than we anticipated. And perhaps this would force us to re-examine our understanding. Well, such an experiment does exist. It's called AMS. And it was launched into orbit a couple of years ago, actually on not the last shuttle outing, but the penultimate space shuttle outing, lifting off. AMS is now affixed to the International Space Station. Here's a picture of it. Now, it's very much in spirit like Anderson's cloud chamber. It's just a higher tech version of it. So it's not a container containing a supersaturated liquid anymore. Inside this experiment, instead, we have layers of silicon-based detectors, which can also detect the path when a charged particle moves through it, but the difference is they can digitize that information, and they can send that information in real time, rapidly, without having to be reset all the time. This experiment also has a magnet, so it can tell the difference between positively and negatively charged particles, and it also has some additional detectors that measure particle energy, and also the type of particle that you're looking at. Is it a proton? Is it an electron? That sort of information. Now, because it's a little more involved than Anderson's cloud chamber, it's a little bigger. It weighs about 8,500 kilograms, which is, don't stand underneath it for any length of time. And it's a little bit larger. Anderson's cloud chamber was a few centimeters in size. I think the scientific term for the size of AMS is that it's bus-sized, so it's rather larger scale. Now, AMS is already taking data. It's analyzed about 25 billion cosmic rays. And it's looking for antimatter. So what sort of antimatter can you get out in space? Well, there's the type that might exist. Let's say you've got anti-galaxies out there that we haven't noticed yet. Presumably then you would have anti-nuclei hurtling through space, anti-helium nuclei. If those anti-galaxies existed, you might expect to see anti-helium. Now, spacecraft have looked before for anti-helium and they haven't found any yet. But AMS has the ability to look for longer and to look further. So it will look for this, even if no one's seen any evidence for any anti-galaxies at all. Now, what about antimatter that you do expect to be there? You reliably expect to be there? Well, there is one mechanism that generates antimatter that we do know about. And that happens when protons zip through galaxies and they scatter around interstellar gas. And as a byproduct of some of this scattering, you can get positrons, the anti-electrons being produced. Now, these positrons don't have as much energy as the initial protons. They're quite low energy. So what that means is, if you measure cosmic rays and you look at the fraction of positrons to positrons and electrons as a function of energy, you'd expect this ratio to go down as energy increases, simply because this mechanism doesn't give you very many high-energy positrons compared to the high-energy electrons that float around out in space. But there are two other mechanisms that could reverse this behavior, both of whom would be really, really exciting and revolutionary if they occurred. And both of these give you additional sources of antimatter. The first is, imagine there's dark matter out there annihilating. This would give you positrons and electrons, both at high energy. Add that to your ratio, it makes it increase. You might also have astrophysical mechanisms that can do a similar job. Not new physics now, this is the physics that we know about, but behaving in a way that we haven't yet found. Pulsars have extremely strong magnetic fields around them. If we have electrons and positrons being made around the edge, these magnetic fields can rapidly accelerate them and whip them off into space at high energies. And then that's another source of high energy antimatter. Now, there have been a couple of previous experiments that have made measurements of this ratio of positrons to electrons as a function of energy. Very, very interesting experiments. And they've both seen a hint that this fraction rises. The only drawback with these experiments is that they have quite large uncertainties. It's quite easy to confuse positively charged positrons with positively charged protons in these experiments, which are much more numerous. So it's a particular goal of AMS to try and work out whether this is happening or not. So I can give you AMS's latest result right now, based on these 25 billion cosmic rays. Here it is. So on the y-axis, we have this positron fraction I've just been telling you about. And on the x-axis, the energy that you've just seen. The green areas and the blue areas are the previous experimental measurements that I mentioned that indicate this ratio rises. Now, what's new on here are the AMS results, which are the red points, much more precise. And they map out this fraction rising with energy much more nicely. So now we are in no doubt that antimatter, there is more antimatter in the universe than we thought. And there's progressively more antimatter as you go up in energy. Now, we don't know yet whether this is due to dark matter annihilating, whether it's due to pulsars or anything else. We need more data to work that out. We need to work out if this antimatter comes from a particular source, somewhere in the sky, if it's evenly distributed, and that will come in time. The AMS experiment has only analyzed 10% of the data it expects to collect. So with extra data, we can look further up in energy and hopefully discriminate between possible new physics and possible physics that we know about behaving in a new way. That's quite exciting. But it's not the only way that we can understand antimatter. We can also look at it in the laboratory, where things are much more controlled. And I'm now going to mention the other two ways that we look at antimatter. And these are both experiments that are based at CERN, the European Laboratory for Particle Physics. Now, CERN has been researching fundamental physics for almost 60 years now. And it's moved from being a European center to a world center for particle physics, because particle physicists from all over the world, quite literally, come together and collaborate here and work together on huge experiments. And it's an especially exciting place at the moment, as I'm sure you're well aware. It's especially exciting if you're an experimental particle physicist, because it's the home of our most powerful particle accelerator, the Large Hadron Collider, or LHC for short. Now, just in case there's anybody here who hasn't heard of the LHC, it's I have an aerial photograph to describe it to you. The LHC is enormous. It's an amazing engineering feat. It occupies a circular tunnel 27 kilometers long that straddles the border between France and Switzerland near Geneva. So here in the photograph, you can just about see Lake Geneva in the background. The city of Geneva is at this end, and the Alps are in the distance. The French-Swiss border is somewhere around here. Now, of course, you don't see the LHC if you're flying over Geneva, because it's 100 meters underground. And if you go down to visit it, which you can do when we're not taking data. And we're not taking data at the moment, by the way, so now is a very good time if you're round in Geneva and you want to have a look at it. It's free to go and visit. You just have to book it. But if you go and visit, you'll find yourself standing in a tunnel, like you can see behind me. It's about the same diameter as the London Underground, and maybe a little bit cleaner. And it's so large, it's such a large circle that you can just see it curving away in the background, in the distance. You can see that very slight curvature. And you can also see that you'll be standing next to a long chain of blue magnets. And it's these blue magnets that are the heart of the particle accelerator of the Large Hadron Collider. These blue magnets provide the muscle, if you like, to keep the beams in the particle accelerator moving round their circular path. Because what goes on inside the LHC when it's working is that we have two beams of protons that circulate in opposite directions around the ring. And they're accelerated to enormous energies. At design spec, which we haven't reached yet, by the way, we're hoping to when we restart in 2015, at design spec, these protons will be accelerated until they're going at just 20 kilometers an hour less than the speed of light. It's really fast. And once you achieve that, you bring these beams into collision at 4 points around the ring. And we don't just bring these beams into collision once or twice. We do it 40 million times a second when the LHC is operating. And what is really remarkable and wonderful about this, and the reason that it's so very interesting and important for us, is that inside every one of these collisions, for a very tiny instant of time, in a very tiny area of space, what we're actually doing is recreating the very high temperatures of the very early universe, fleetingly. And when I say early, I do mean early. When I say early, I'm talking billionths of a second after the Big Bang. That early. That's what we can experimentally access. Now, if we have colliding beams at 4 points around the ring, the thing to do is to build experiments around these collisions, because then with experiments, we can record what happens. We can build experiments that behave essentially like gigantic three-dimensional digital cameras that take snapshots of these collisions as they occur, that make measurements of the fundamental particles that are produced in collisions as they fly outwards with high energies and cool down and work out what they decay to and so forth. And we digitize this information and record it, and then we analyze it later to see if it matches up with theory or not. Now, the interesting point from the point of view of researching antimatter is that collisions at the LHC make matter fundamental particles and antimatter fundamental particles. That means we can isolate samples of both, and we can make measurements of both, and we can directly see if matter and antimatter show differences at this very smallest level. So we can isolate snapshots, such as this one. Yeah, here we go. We can look for matter behaving in a particular way inside our experiments, record this, and then look afterwards to see how many of those snapshots are matter, how many of them are antimatter. Do we see the same rate? Are they different? Now, I work on the experiment at the LHC, which is really designed to look into this question. It's an experiment called LHCb. This is a picture of it. It's not very photogenic compared to some of the other particle detectors you might have seen at the LHC. And that's because it's a different shape. It's instrumented in a different way. It's actually end-on in the experimental cavern. It's pointing in this direction. You can't see it because it's surrounded by so much scaffolding, so many staircases to enable us to walk around it and fix bits when they go wrong. So perhaps the easiest way of seeing it is as a schematic. So here we go. So imagine, if you will, our proton beams running through the length of the experiment. Now, just like AMS, this experiment is really just an updated high-tech version of Anderson's cloud chamber. Around the collision point of the beams, which is here, we have detectors, silicon detectors, that make measurements of the tracks of charged particles as they fly through. We have a big magnet that tells us whether we have positively or negatively charged particles. We have detectors that measure the energy of the particles passing through, and detectors that, just like AMS, can identify the different types of particles that we have passing through. So you see that AMS is really a particle physics experiment, even if it's stuck out in orbit around the Earth. You'll also note that now we've expanded our scale again, and instead of being bus-sized, LHCb is, well, I don't know, super bus size, stretch bus size, 20 meters long. It's absolutely enormous. Now, the reason it has this particular shape, well, the clue's in the name. LHCb is called LHCb, not because it came second or anything like that, but because it studies the property of the B quark, one of the quarks, one of the fundamental particles. And the reason that we chose to study this particular fundamental particle is that for reasons we don't understand, matter and antimatter versions of the B quark behave most differently. And that makes it a really good laboratory for studying the effects of matter and antimatter differences, because they're just easiest to measure. The other thing that's handy for us is that B quarks, when they're produced in collisions, they usually fly along the same direction of the beam, and this accounts for the particular shape that we've built our experiment in. The other thing that's really handy about the B that helps us isolate it from all the other millions of things happening inside the LHC when we have collisions that we can't record all of them. We can only record about 1,000 of the 40 million happening all the time, is that Bs have a very distinctive experimental signature. They only live for a very small time before they decay to other particles. But that time, that lifetime, is just long enough for them to fly a few millimeters or a few centimeters through our experiment. And we can deduce that in real time because we have silicon detectors that are so precise, and here's a picture of one. They're so precise that they can tell the position of a charged particle passing through them to within 1/10 of the thickness of your hair. And we have a whole series of these detectors that particles pass through that enable us to reconstruct their paths and then to determine whether they came from the same collision as everything else or whether they came from somewhere a little distant, which is the hallmark of coming from a B, and that's what we want to control and remember. So the way that LHCb investigates antimatter is it takes a type of B decay that's easy to find experimentally. So here's an example. Here we're looking at a type of particle containing a B quark called a B sub S meson. That's just a B quark and an S quark united together. And it decays quickly to a particle called a kaon and a particle called a pion and gives us a snapshot that looks something like the one behind me. It's easy for us to identify this in our experiment. So we just collect as many as we can. And once we've collected them, we look at the charges, the electrical charges of the kaon and the pion, because those are different for matter and antimatter. And that allows us to count how many matter B sub S mesons we have and how many antimatter B sub S mesons we have. We're just looking to see if there's a difference or not. That's all we want to see. And in fact, this particular particle wasn't really nothing much was known about it before we started taking data because it's only produced very, very rarely. And it was only this summer that we were able to make our first measurement of matter and antimatter in this system. This is what we found. It doesn't look particularly glamorous, but what it shows you is the number of B sub S mesons, the matter ones, that we reconstructed on the left, and that's shown by this green area here, and the number of antimatter versions on the right, shown by that green bump there. Now, I know that doesn't look too impressive because we only have about 1,000 of them altogether in the data that we've analyzed. And to put it in context, it took 70 trillion proton-proton collisions to just get this many. It takes a long time. But if you look at the relative heights of matter and antimatter, there's a difference. We're seeing more matter than antimatter. In this particular case, we're seeing about 25% more matter than antimatter. That is a clear difference. And that was something that had not been observed before, which we could do and did this summer. Now, that was great, and we could compare that to what we expected to see. And unfortunately, it was exactly what we expected to see. And I'll tell you why that was bad news in a minute. So this is the angle that my particular experiment brings onto this search for antimatter. It's trying to understand it in terms of quarks, fundamental particles, and it can do that not just for B quarks, but just very recently we've discovered we can do it for another type of quark, the charm quark, where we don't expect to see any difference between matter and antimatter. And we don't. It's wonderful, but not that wonderful. So we can look out in space, we can look at fundamental particles. There's one other way we can investigate antimatter, and that's by looking at anti-atoms. And this also happens at CERN, but not at the Large Hadron Collider, at another particle accelerator, which is the rather wonderfully named antiproton decelerator. And what happens here is that we generate antiprotons, and we cool them down, we slow them down, and we bombard them with positrons. And very occasionally, a positron and a and an antiproton will fall into orbit around each other and form an anti-hydrogen atom. And our idea here is, because hydrogen atoms are so well known, if we can make anti-hydrogen and measure the properties of anti-hydrogen, we've got a very detailed system that we know about to compare it to, and we can look for differences there. And one experiment at this facility, the ALPHA experiment, has devoted a lot of time in trying to keep these anti-atoms in one place long enough to make measurements. Now, this is a problem because the other two experiments I've told you about make measurements of antimatter, but only once it's been and gone. You don't see it in situ, and you can't make measurements of it as it exists. What ALPHA tries to do is trap anti-hydrogen atoms and make measurements of them while they're still there. Now, trapping anti-hydrogen is really tricky because it's neutral. You can't apply an electric field across it to hold it in suspension, and you know the moment it touches anything, there are protons and electrons in anything it touches. It's just going to annihilate like a flash. And indeed, it will be a flash. So what ALPHA have developed is something called an anti-hydrogen trap, a magnetic bottle. It's shown here, and it has immensely clever magnetic fields that keep the anti-hydrogens in suspension because they interact with the magnetic spins of the particles inside the anti-atoms and just keep them away from the walls of the container. Now, ALPHA's only done this for a few hundred anti-hydrogen atoms so far, and it's managed to hold them in suspension for about 15 minutes. Now, I don't know if any of you have read Dan Brown's book, Angels and Demons, or seen the film. If you do, then you'll be aware that, according to Dan Brown, CERN is capable of manufacturing enough antimatter to destroy the Vatican and of storing it in canisters like this that run off batteries for 24 hours or so. Well, we're nowhere near that at CERN. The best we can do is ALPHA and 400 anti-hydrogen atoms for 15 minutes. But at least it's a start. And ALPHA has proved that we have the technology to be able to start making measurements. So what measurements can you make with anti-hydrogen? Well, it's rare to get, it takes a long time, and we don't have many of them, so we haven't been able to do precise measurements yet. But what we have done is tested gravity on antimatter. Now here's a thought. How does gravity affect antimatter? Does it go down or up? I mean, you think it would go down because antimatter has mass, but antimatter is so weird, you never know. You'd better find out. And you can do very simple things like turn off the magnetic field in that trap and look to see whether your anti-atoms fall down and annihilate on the bottom of the trap, or if they float upwards and annihilate up there. And that gives you a fix on how they behave under gravity. So that we've had a first look at that, but with not enough precision to say anything particular. That's something that we'll need more anti-atoms to look at. And in the future, we also want to test the structure of anti-hydrogen. We want to look to see if positrons orbiting the nucleus have the same energies as electrons orbiting the hydrogen nucleus, so whether there's a difference there too. And the reason that we're looking for differences is, I remind you, that we really genuinely do not understand the nature of antimatter at all. And it's only by trying to find differences wherever you can that you might find something that gives you a clue to that ultimate nature that you're trying to understand, something that will just give you a glimpse of the theory that you're going to need to describe it, that will then revolutionize your understanding of the universe. So those are our experiments that really are state-of-the-art at investigating antimatter. And what have they told us? Well, you've seen that they're in their early stages, all of them. You've seen that AMS has only analyzed 10% of its data set, and it's seen something really quite compelling. There's more antimatter out there than we thought originally. It must be produced by a mechanism that we don't yet understand, but we don't know whether this is a new type of physics making it occur, or astrophysical processes that we don't yet fully understand, but which are standard physics. That all has to be understood. You've seen that ALPHA is able to make anti-hydrogen atoms and store them to make measurements, but we haven't yet made them with any precision. So in fact, most of what we know comes from experiments like LHCb and its predecessors that investigate matter and antimatter at the level of fundamental particles, and then make a test, a direct test, of this parameterization, this description that I told you we'd put into the standard model of particle physics to try and describe antimatter, to describe our data. That is the only real test of antimatter we've been able to perform so far. So let me show you how we're doing with that one. So in the standard model, there are just 4 numbers that parameterize how antimatter behaves and how quarks behave under the weak force compared to the other forces. Now the reason we do that is because matter and antimatter only seem to behave differently under the weak force, not the other forces. We don't know why, it's an observation. And so that behavior is just included in these 4 numbers. So the idea is whenever we make a measurement that is sensitive to any of these numbers, we can extract values for them from our measurements. If we can do this from a variety of measurements, we can compare the values that we've extracted to see if they're consistent with each other or not. If they're consistent with each other, it means that even though we're fairly dumb with the way we're describing antimatter by just having a number, it means it works. And that's sufficient to describe data, even if it doesn't explain it. If these values don't coincide at all, it tells you that your understanding's rubbish and you better go away and think again. And, that would be quite exciting too. You can't lose in particle physics. You either discover or you discover more that you don't know. So, what have we found for that number? Well, let's have a look. This picture is a summary of everything that we have found out and compared to the standard model. Now, what it shows you are colored areas which are the possible values for these standard model parameters that we've extracted from a whole series of different experimental measurements. We've made measurements, direct measurements of matter and antimatter behaving differently. We've made measurements of matter oscillating into its antimatter counterpart and back again. We've made measurements of matter particles decaying, of antimatter particles decaying. All of those give us information that goes into this colored plot. Now, there is one point in this plot where all of these colored regions coincide, right here. And what that means is that each one of our experimental measurements has a value for the matter-antimatter difference, which is consistent with each other. The whole framework of the standard model with these extra 4 numbers in seems to work at describing our data. It does a really good job at describing our data. Really, really, really brilliant. The fact that you can perform experiments on very, very different types of particles in very different ways, and they all give you the same information back about how different matter and antimatter is really compelling. It looks like we really understand our data. We really understand how quarks and antiquarks behave. So let's put that into practice, because what we can do is take the amount of matter we know that we see around us, and this difference between matter and antimatter that we see in the standard model, and we can work it backwards to estimate how much antimatter there should be at the beginning of the universe. Well, if you do that, if you go through the procedure, it's a bit shocking, because you don't find half a universe's worth of antimatter at all. It's far less than that. What this implies is that there's only one galaxy's worth of antimatter. We've fallen short quite a lot. There's quite clearly a lot of antimatter that's unaccounted for. So we might well understand the behavior of quarks and antiquarks really, really brilliantly, but that's not enough to describe the evolution of the universe. That is still a mystery. So where is this answer going to come from? If the best we can do is to only understand a teensy fraction of the difference that must exist if you go from half a universe of antimatter to a universe of mainly matter, then where can we find answers? Well, it's obviously where we haven't looked yet. And there are many places where this can be. I've only talked about quarks. It might be that in particles we haven't been able to explore very much yet, neutrinos, which are very, very, very difficult to detect experimentally. That's why we don't know very much about them. It might be that neutrinos exhibit a much greater difference in behavior between matter and antimatter versions than quarks. Well, we hope our next generation of neutrino experiments that are being designed at the moment and constructed at the moment might be able to make the first measurements so we can find this out. At the moment, we genuinely don't know. We don't even know what the anti-version of a neutrino is. It might even be the same as the neutrino. Anything is possible. There's also the possibility that there's new physics out there. And by new physics, what I mean is new physical processes that we haven't yet seen. Physical processes that arise from a deeper theory of nature than the standard model. And there are candidate theories that are around on the market at the moment that we test on our experiments. And one of the most popular new theories that we test is a theory called supersymmetry. Now, supersymmetry has actually been around since the 1970s. And although we haven't found any experimental evidence for it yet, it's such an attractive theory that we're reluctant to let go of it. And what supersymmetry does is it takes the standard model and it extends it by adding a new symmetry in nature, a new connection, a new simplicity. And it's a connection between force and matter. And the way that supersymmetry does that, practically speaking, is it predicts the existence of a whole lot more new particles. Supersymmetric partners of every particle we know about, such that the supersymmetric partners of matter particles behave like force-carrying particles, and the supersymmetric partners of force-carrying particles behave like matter particles. Now, supersymmetry doesn't have a well-defined explanation of antimatter and matter-antimatter differences inside it, but it could be incorporated in it. It could describe it. It's possible. And perhaps those AMS results that we saw before, that extra antimatter out in space, well, that could be linked to supersymmetry. Because one other attractive aspect of this theory is that the lightest one of these new supersymmetric particles that's predicted is a really good candidate for what dark matter might be made of. So that's why we continuously look for any evidence that this theory is correct. But that is in the future. So what is the outlook for making progress with antimatter? I've shown you what antimatter is, how it fits into our understanding of the universe, why it's important, and that we know so little. And I've also shown you how we're trying to explore it. So the future for antimatter is, in essence, a bit more of the same, because we're only at the start of these experimental investigations. AMS has 90% of its data to have a look at. LHCb has the rest of the LHC's worth of data to look at. And as we're going to go up and double our energies when we restart in 2015, there's a whole lot more of the universe that we can then explore, earlier times and so forth. We can also look not just for CP violation, but for new physics as well, any evidence there that can then be linked to antimatter. And we saw alpha as well. Now, alpha hasn't seen very many antihydrogen atoms, but it's going to restart next year with an improved trap and generate far more. And then we have neutrinos. We might find out more about neutrinos. Who knows? It's in the future. So my last word in this, our search for understanding antimatter and how on earth it made the difference to make the universe evolve from the Big Bang to now, is that this search is one of the biggest questions in physics. It's one of the biggest questions we're trying to answer in our experiments. So stay tuned. We're finding out evidence as fast as we can. And as soon as we make any discoveries, as soon as we move our understanding forwards, then we're quite definitely going to tell you all about it. Thank you.